let's make a start. Okay, so where we left off last was we're getting into the application section, or the extended response section, I guess, of the chapter 11. This is all your integration applications. So we're going to go through those, starting at question 4, since we had finished, or at least mostly finished, question 3. So let's have a look. Referring to the screen share, it is thought that the temperature theta, that's a bit interesting, giving theta to temperature, usually give theta to angle. But anyway, temperature theta of a piece of charcoal will increase at d theta dt, given by a particular equation. So we have essentially a derivative or a rate of change equation for the rate of change of temperature. Theta is degrees, T is going to be minutes. Okay. Part A. If the charcoal starts at a temperature of 30 degrees, find the expected temperature of the charcoal after 3 minutes. Okay, so a couple of things worth pointing out here. Expected temperature is another way of essentially saying the expected value of a certain function. What's worth pointing out further is that the equation that we're given is a rate, right? The temperature will increase at a rate of d theta dt. So we currently have a rate equation. We're trying to find a quantity as a result, or the expected quantity. And so there's a couple of ways you can go about this. Have a read of what's going on there. Let me know if there's any things that come to mind as to how we might go about this. In the meanwhile, I'll define it in our CAS. Currently have the rate at which temperature is increasing. We're told the starting value of the temperature starts at temperature of 30 degrees. We want to find out what the temperature would be after 3 minutes. So a couple of ways of doing this. One is probably the most natural way to go about this would be to convert our rate of change equation, our derivative equation, into one that has the actual quantity itself, right? Expected temperature is a temperature value, not a rate at which temperature is increasing. And so for that reason, one thing you could do here is just anti-diff to get back to the actual equation itself. So if we anti-diff our function, anti-diff hx dx, we're going to get the generic anti-diff, the indefinite integral of that. There is an implied plus c whenever you do an anti-diff. Right, so this technically has a plus c in there as well. Because we're told the charcoal starts at a temperature of 30 degrees, that is a known point on this now temperature function. We've gone from a rate of change of temperature to now a temperature function. And because we're told the charcoal starts at a temperature of 30 degrees, that means that at time t equals 0, the temperature should be 30. Or in other words, if I sub in the point 30, 0, oh sorry, the other way around, the x being 0 and the y being 30, I'll be able to solve for my c. So we'll do exactly that. Temperature of 30 is equal to that when we have our x equal to 0, and we'll solve for the c. That's going to get our integration constant. We now have the properly anti-diffed function. I of x, which I'm going to refer to as the temperature equation, and we're going to put in that constant of integration, the solved constant of integration. Any questions so far? What we've done at this point is convert our rate equation into a temperature equation using the actual quantity rather than the rate at which that quantity is increasing. and we were told an initial value, so we could even get more specific with what the full antidiff of that was. Are there any questions so far regarding what's been done? From there, the rest of this question now becomes fairly trivial. Find the expected temperature after 3 minutes. Well, we're just going to shove in t equals 3, or at least in the CAS's case, x equals 3. Do we have to do... It doesn't say anything about decimal places, so I guess this would be what you give as your final answer. Although, just for the sake of a readable answer, that's what you'd be looking at as far as your temperature value, the final temperature value. This one didn't say anything about decimal places, so you do give this top one as your answer, and you give it in degrees Celsius. You put a degree symbol with C right after it. That's probably the most natural way of solving this. Are there any questions about that? 4a. Found the expected temperature after 3 minutes. Yeah, and if I go too fast at all, feel free to even put a message in the chat and I'll go back on explaining more things. The other way that I was thinking, which is a little bit less conventional, is to understand that a rate equation, actually no, I don't think that's going to work, is it? Because I was going to say something to the effect of, well, if we know the rate at which something is increasing for different values of time, then if we subbed in 3 into that, we would know the rate, but it wouldn't really work. I was going to say something to the effect of plug in t equals 3 into your rate equation and then add the result to the starting temperature of 30. That doesn't actually quite work now that I think about it deeper. So yeah, this would be the only way to go about it. Antidiff, get your function, and then go from there. Part B is trivial at this point now. Sketch the graph of theta against t. What we have, that I of x there in our CAS, is theta of t. And so, this being tech active, you can literally just go to the graphing tool and do exactly that. It'll just be an exponential, won't be anything crazy. You don't even really need the CAS to do this. I'll fix the window settings in a moment, but first just to explore a little bit about what we might expect. This is a positive exponential. It's going to shoot up and to the right, and it's got a asymptote here, the horizontal asymptote, 385 over 13. I'll just quickly control enter that just to get the actual value. Okay, so maybe I'll set my domain as something like, I don't know, yeah, higher than 50, let's say. That's not it. This is. Cool. Let's, what time? Yeah, time values are still relatively tiny, so we'll keep it 0 to 10. We'll just shoot this up to, say, 100. Yeah, there we go. And yeah, that'll be more or less what we expect. Cool. At what time does the temperature of the charcoal reach 500 degrees Celsius? That's part C. Again, this is a fairly trivial question as long as we understand what function to use. Any suggestions on how we're going to solve part C? At this point we have our theta function, our temperature function. At what time does temperature reach 500? Okay, so this I of x that we have in our CAD.
Do we just grab the integral? Grab the integral?
Yes, so the integral,
yeah.
the integral was this I of x here. We had a graph for that.
Yeah.
That was our theta against t. Yeah. And yeah, the integral is exactly what we're looking for there, because we've gone from the rate equation to the actual temperature itself, the quantity. And so when it comes to finding temperature at a specific time, you know, quantity at time, you would now use the integral equation. And from there it's just a quick CAS solve, right? Set your y value to 500 and solve for t, or in this case x. 500 equals function, comma, x. That'll be the actual time you give because it doesn't say anything about decimal places, but just for our sake, that's going to be roughly 2.7-ish minutes. Cool. Okay, question. Scroll up a bit more on the screen share. Yeah. So we're currently up to question 4 here, and we've done up to part C at this point. Because we ended up finishing off the last bit of this. Well, kind of, there's a little bit of this left, but we got the gist of what was necessary for that previous question. Okay, is that scrolled up enough? Let me know, otherwise. Next up, average rate of increase of temperature from T = 1 to T = 2. So the wording around this, I know, throws a lot of people. You know, average rate of increase. There's two concepts that are very closely tied to the keyword average. In fact, when we start looking at probability, there's going to be even more concepts tied to the word average. But for now, pre-probability, there's at least two main concepts tied to the word average. Average rate of increase, keyword rate, will tell you which of those concepts you need. Would D be?
Is it average rate of change?
Yes, this will be average rate of change. So average rate of increase of temperature from T = 1 to T = 2. Rate of change, rate of increase, absolutely. Yeah. So we now know we're doing what is effectively the rise of a run. Y2 take Y1 and X2 take X1. The straight line gradient. The next challenging bit is to figure out which of those functions, the derivative or the antidiff, which of those are we actually applying the average rate of change equation to. That's also a challenging bit.
The derivative?
The derivative? Why derivative?
Because it is the average rate of change.
So the derivative itself is an equation which is itself the rate of change. So the challenge or the problem with putting it on the derivative specifically is if you do the average rate of change of the derivative, what you're doing there is finding the average rate of change of the rate of change. Rather, in this case, you're trying to find the average rate of change of temperature. So it's one of those things where there's 2 points of failure. There's one where you pick the wrong equation to start with, and there's one where you pick the wrong function to apply it to. So I can imagine why these start getting a lot more challenging. There's a couple of different points of failure there. That's not to say that you can't use the derivative formula. You actually can. And there's a really... yeah, there's a way to use this derivative formula anyway. But for now, we'll focus on probably what's the most expected way of going about things, which is, because it says find the average rate of change, increase, of temperature, because it's referring to the temperature as the thing you're trying to find the average of, you put it to the temperature equation, which would be the antidiff. Yeah, Taihan?
Yeah, I was just thinking a little bit about how I could solve it.
Yeah.
Could I just go through it?
Go for it, man. Yeah.
Okay, so I was thinking, so yeah, obviously if we're thinking about average rate of increase, which is just your average rate of change.
Yep.
So I think so the output's temperature and the input's time, right?
Yeah, precisely. That's one way to think about it. Yeah.
Okay, so we're finding we need the temperature at T1 and the temperature at T2 because the denominator of the formula would just be 2 minus 1, right?
Yeah, it'll just be 2 minus 1. Yeah, precisely. Yeah.
And I think for the d of theta over dt, I think that itself is how fast the temperature is changing, right?
It is. Yeah, it's a rate equation itself.
Yep. So I think then we undo the derivative, so we just integrate that, right?
We integrate. So you ended up joining a bit late. We did in part A the antidiff of that already.
Okay.
That's going to be that's going to be the I of x that we have here. But yes, that is exactly what you would need to do if you didn't see part A. Yeah.
Yeah. And then I was thinking you know that the question says the charcoal starts at 30 degrees, so you can just use those values.
Yeah, to get the proper
0. Yeah.
So I'll show you the working out for that just so you can see it. You already explained exactly how it works anyway, but just for your own sake for the CAS. So first thing we did was anti-diff the rate equation, and we chucked in that plus c because the CAS doesn't naturally do that for whatever reason. And then from there, yeah, subbing in that point exactly as you said to solve for that integration constant. We now have our proper I of x, or the theta bracket t equation. And so yeah, the rest of that is exactly as you described, which is we want to find the temperatures at those, whoops, not h but I.
Yeah, because I think what I got was theta t equals 30 over 1, 30 plus 1 over 2.6, and then the e to the power of 2.6 t minus 1.
What you got for the anti-diff?
No, for like the rewritten equation, I got theta of t equals 30 plus 1 over 2.6 brackets e to the power of 2.6 t minus 1. And then I
mean, you got a decimal, I guess I got a fraction, so maybe you got similar to me.
Yeah.
But yeah, like if you do your AROC, you should get 64-ish.
Yeah, I got that.
You got that? Awesome.
Yeah.
Taihan, you're still there with it as well, yeah?
Yeah.
Okay, cool. We're all on the same page with the functions. Now, do you want to see another way of doing this, or are these questions complicated enough to where you just want to have one way of doing it?
I would like to see another way.
Okay, another way of doing it. So, one of the, again, I said at the beginning, this keyword average here can refer to two separate things. The other thing is the average value equation, where we use the integral, right? We do like 1 over the length and then the integral over that time. Average rate of change can be found by applying the average value equation to the derivative, because average value finds the average y value of the function. But when the y value is itself a rate, what you've essentially done is applied the average rate of change. So there's two ways of doing this. One is convert this into its back to the quantity itself, and then average rate of change, the rise over run, or start with the derivative and apply the average value to that, because the value we're talking about in that context is itself a rate. The math is identical, and the reason why is because when you're doing average value, when you're doing integration, when you're doing a definite integral, the first step is the antidiff, and the second step is subbing in the values, the t equals 1, the t equals 2. It's functionally the same thing as what we just did. So let's go ahead and try that. So it's 1 over the length, so the length is from 2 to 1, so basically nothing, but just putting it there to show the full formula. And then it's the integral of the original, which in this case is the derivative, because we're applying it to a rate. And if we do that, and I control enter, you'll see it spits out the exact same thing. This is sort of why I was hesitating to mention it at all, because it's kind of already complicated enough to know when to use what. So pick one of those to go with, because the reality is you should be able to do either in pretty much any circumstance. Like maybe if this part A didn't exist, you would kind of have to... No, it still wouldn't matter because the plus C is just a constant. Rates don't have anything to do with the vertical translation. Yeah, in every circumstance, I'll stand by that. In every circumstance, you can do either of those methods. It's just, I guess, whatever's most immediately available. And by the time we get to part D, we've got both functions anyway. So, your choice of preference. Do I need to explain any one of those in any more detail? Because, again, there's a fair few ways to mess this up. If not, all good. Let's have a look at the next one, part 5. Velocity equation. Now, yes, this says this is written like a derivative, but we've got to remember that the variable x is defined as distance. So when we have dx dt, we're having the rate of change of distance over time, which itself is velocity. Right, the way we calculate speeds is we say, hey, here's position 1, here's position 2, it took that long to get there, that's our speed. So dx dt, although it looks like a derivative, which it is, because we're talking about position, velocity, acceleration, another word for that would be the velocity equation. Okay, so t is going to be in seconds, and velocity is meters per second, because x is meters. What is initial velocity of the particle? Getting into kinematics now. Although, I wonder if it's going to actually matter whether it's kinematics or not. Should still be presumably the same idea. I'll start defining the function. It does have this v in here, but just remember the v is actually defined 5 by 10 to the 4. Function equals 5 by 10 to the 4 e to the minus t, or in my case, e to the minus x. Okay, I think that'll be good. That's our velocity equation. What is initial velocity of the particle? Keyword initial. We've seen that before in question 4. Kind of
T
actually.
equals to 0.
T equals to 0, yeah. Initial, starting, anything like that is implying t equals 0. Yeah, and since we have a velocity equation, well, if I shove in time 0 into my velocity equation, I should get whatever velocity is at time 0. Which, well, if we know anything about exponentials, we know it's just going to be the leading coefficient. It's the initial value. Easy. Just make sure you give the units when you actually write it down. Meters per second. You can do m over s, or you can do the physics way, where you do ms power minus 1. I think I still have that habit occasionally. This one I know I've seen people get tripped up with a little bit. It's not too complicated once you understand what it's saying. What happens to velocity as t approaches infinity? Or I guess as time increases to heat death of the universe. There's a fair few ways you could actually go about this one, especially with CAS.
I mean, wouldn't this be a decomposing graph?
It sure would, yeah. You can
Yeah, so it just approaches 0.
approach a 0, precisely, yeah. Why 0 specifically?
Because it's e to the negative x, and e to the x is an exponential.
Yep.
So e to the negative x, since the negative is on the x and not the whole function, it's going to be flipped on the y-axis.
Yes.
So it's a decomposing graph.
That's exactly right, yeah. It's going to decay to its asymptote. And in this case, we can see the asymptote is going to be 0 because there's no vertical translation applied to it. So yeah, you can just analyze the graph, or at least the function itself, and using your function knowledge, you can determine that without even needing any calculation whatsoever. If, for whatever reason, this function looked a lot more challenging, there's a few more ways to do this. In the CAS, you can literally plug in infinity into your function and see what happens. The infinity symbol is with the pi button. So the same way you put pi in is the same way you can put infinity in there. And if you forget that, then the other thing you can do is actually apply a limit, although this is just kind of just a worse way of doing things, because you just put in the limit as x approaches infinity of the function, and the same thing will happen. I think I just missed your explanation. Why do add the multiplication? That's just me defining the function. So if you have a look at the question 5 function, v e to the minus t, that is v multiplied by e to the minus t. So why do I add the multiplication? Yeah, I mean that's just how it was written. And v was 5 by 10 to the 4 itself. Am I missing something of that question, or? Because yeah, I just ripped that straight out of question 5. The left side of the part is a derivative, the right side is the actual equation. Oh yeah, cool. Cool. So why am I just defining the? Why am I just using the derivative itself and not trying to like anti-diff, for instance? So the reason why is if we have a look at what the variables are defined as, we've got x as distance and t as time. All of these are caring about velocity. And so we haven't done kinematics for a while. The stack of kinematics is such that if you diff your position, so your distance equation, you get down to velocity. And if you were to diff that again, you'll get to acceleration. So since these are all talking about velocity, we're using the velocity equation. Now this could have said v of t equals this, but for whatever reason, they've decided to use the derivative notation by calling it the derivative of the position function rather than just velocity. They mean the same thing though. Does that answer your question? Why do we combine them in defining of the equation? Why do we combine them? I'm not fully certain. So as in, like this left-hand side doesn't appear on the right-hand side at all. So if I go to the function definition, which I have highlighted on my CAS, it's 5 by 10 to the 4 times e to the minus x. Where I got 5 by 10 to the 4 was this thing on the right-hand side here, which said v is that. They just didn't want to write 5 by 10 to the 4 on that for some reason. So the function itself is v times e to the minus t. The v part is the 5 by 10 to the 4, and it's being multiplied by e to the minus t, which in my case I've written e to the minus x instead. Is that a bit clearer?
Yeah, okay, that makes more sense. Cause I know I was getting confused because you had the v and then you had the e to the power of negative t on the other side. I was like, I don't know, I just didn't clock it.
Oh yes, yeah. It's a bit weird to have it defined in line rather than maybe like in the next carriage return underneath. But yeah, that's what they meant there. Cool. Okay, what do we do? So, oh yeah, anyhow.
Why is there like is x dx dt the velocity?
It is, yeah. So if you see x is defined as distance and t is defined as seconds, then dx dt would be rate of change of position, which by definition is velocity.
Okay, so that's speed. Yeah.
Yeah. So speed would be the scalar, just for the physics.
Yeah.
And
yeah.
because it's written, I guess it is distance here, isn't it? Because this function, yeah, is this velocity or speed? Well, it's calling it by definition a velocity equation, so I guess we can just probably assume that perhaps they should have called this the position. Because it says at the header that this is the velocity, dx dt is the velocity.
Okay, so why are there like two velocity equations?
I don't believe. Oh, this is a constant. This is the constant v.
Oh, okay. I just realized that. Yeah. Okay.
Okay, cool. That's the bit that's confusing everyone. Got it. Okay. Yeah, that's just the constant v, which is that coefficient. Cool. Okay, next up. How far will the particle travel between t equals 0 and t equals 20? So things at play here, it's going to be time values because it's t, and how far will be distances, right? So far we have a velocity equation and that's it. So we need to somehow get position, which I mentioned the stack already, how position, velocity and acceleration are all related to each other. Let's see if someone can just rattle it off. How are we going to get back to position?
They're antidiff.
Antidiff, yeah, precisely. So let's go ahead and antidiff a function. H of x dx. That's going to get us the indefinite, excuse me, the indefinite integral. It's not fully completed. There is a plus c involved in there. How are we going to get our plus c?
We do it from 0 and 20.
Yeah. So we will
0 to 20. Yeah.
with our, like, to answer fully part C, once we get the proper position equation, we will be integrating, oh sorry, not integrating, we'll be finding the difference between 0 and 20. But my suggestion here is that we don't actually have the position equation just yet. We have most of it. There's still a plus C.
Okay, can we just integrate it with those endpoints, like 0 and 20?
Oh, okay, no, I get you what you mean now. So integrating, so literally just definite integral 0 to 20 of the derivative? Yeah, okay, that actually works. Yeah, you're right. So we talked about this earlier when it came to, let me just do it real quick. So 0 to 20. And is that about right? How far the particle travel? Sounds about right. Cool. Yeah, so we talked about this with our applications of integration, which was like, what does area under a curve actually mean? And what it means is going to depend on the function that you start with, where you apply your definite integral to. So, in fact, I've said this a few times. Nihal, you got it. Do you want to give a go at explaining why definite integral of this works out the way it does?
Okay, so that gives the area. Okay, so that's the area between, between the graph and the x-axis.
Yep.
So that's like if it's the velocity equation, it will give the total accumulated distance or change in position.
That is what it does. Yeah.
Yeah.
Do you know why it is why it is that way?
Yeah.
Okay.
Maybe.
Why in your mind is that the case? Why is it that area under the graph in this case is accumulated distance?
Okay, so how I see it is like, so it's the accumulated y values.
Yeah.
That's how I kind of imagined it.
Sure. That's
Yeah.
fair.
Yeah, I don't know how to explain it.
No, that's fair. That's fair. I was just curious if you had an idea on how you wanted to explain it, because it is correct. I just wanted to see how you guys understand it. So the way that I would explain this would be, if you think about what a definite integral is, it's done in two parts. The first part is itself the antidiff, right? You antidiff whatever function it is, and when you antidiff your velocity, you should get to position. To complete the antidiff, complete the definite integral rather, you now do the, let's say I is the antidiff function, you now do I of top minus I of bottom. Or in other words, because I is position, and you're finding position at 20 minus position at 0, yes, you did a definite integral, but if you think about how the function changes and what you're shoving into that function, you've gone to position and you've subtracted two position values from each other. Or in other words, you found the difference of position between two separate times. And so that's the most succinct way of doing it, which I actually overlooked, so nice of you to pick up there, which is simply just integrate as definite integral between 0 and 20 of your derivative. Do I need to explain that in any more detail for anyone here? I will go through another way of going about it.
On your CAS, do you use float 12 or whatever?
I got to float something. Let's, is it float 6 maybe?
Yeah, because I used float 6 and it came up with exactly 50,000.
I just got regular float.
Oh, okay.
Yeah, so you wouldn't want to control enter this anyway. I was just doing that for the value. it doesn't say anything about decimals, so you'd actually just want to leave it as that. But yeah, you're rounding to any number of precision there, you'll probably hit 50,000. Yeah.
Mm-hmm.
But okay, so that's one way of doing it. The other was to essentially do the exact same thing but in two separate parts, which was, okay, I know that I have my velocity, I need to get to position. So I anti-diff. I now need to figure out what my plus c is going to be, which again, you're just going to sub in the known point. We know the initial velocity was 50,000, so at time t equals 0, you should get 50,000, which is why the c is going to end up being 50,000. We now have our position equation. We now do sub in our t equals 20, sub in our t equals 0, and do the subtraction between them. And so the reason we didn't have to do that for the definite integral is because now that I'm looking at it, it's just a constant. So whenever you have a fixed value applied to both, when you do subtraction, you're just finding the difference between them. So if you're adding the same amount to both anyway, it's like saying difference between 2 and 1 is 1, difference between 10,000 and 9,999 still 1, because you're adding the same amount to both sides. So yeah, good on you for finding a more succinct way of doing it. Cool. Part D is forcing us to do the anti-diff anyway, find an expression of x in terms of t. So I think we'll just ignore that one. We've got it in front of us right now. We just explored it right now. And then sketching that graph. Like, this won't be anything crazy. Still just a decaying exponential with a horizontal asymptote of the 50,000 that we knew from before. Cool. That's about it. Next up, oh, these ones. It's been a while since we've done these. Diff function, hence show. Gee, this is a nasty hence show. Let's see how we go with this one. Okay, the diff we can at least do with the CAS, because this is tech active. If you did need to diff this by hand, by the way, what kinds of diff rules would you be using? What's going to be applicable?
Rules of like e to the power of something, like
oh yes,
the
sorry,
diff of that, and
I meant more as in like product quotient rule or chain rule.
Oh.
Which one's going to be applicable
yeah,
here?
just product.
Yeah, just product and a little
Product
bit of
and chain.
Yeah, there you go. Because yeah, like you do have in your formula sheet, you do have these basic chain rules already baked in, but they are in still fact. They are fact. Say that again. They are still in fact chain rules. But yeah, we have tech active, so we're just going to go ahead and actually I'm not even going to define them just yet. We'll just diff them, because it is a show that we're going to have to start writing some things out anyway. E minus 3x times sine 2x. Oh, Jesus. Yeah, I should have expected it to be that big. And cos 2x. Yeah, that's fine. Cool. Alright. Big nasty diffs. Let me start copying that down. Okay. So we're going to be using these results to work with these related integrals. So let me go ahead and try copy those down. Maybe I'll turn up the brightness a bit more. Or a lot more. Jeez. Okay, cool. So first one we had was d dx of e minus 3x sine 2x. And we know that one is equal to... Geez, I'm going to be here all day. So while I'm writing these down, just assume that you do have these diff equations. You'll notice that there are going to be some similarities. Have a think about how those similarities might play a role in in answering the next couple of integral related questions. E minus 3x sine 2x. Okay, let me me just double check I got those right. Yep, and yep. Now, I think I can just copy paste this. And then just change the bits that need to be changed. Oh, let me come. Oh, okay, good. Yes! Saving time. Cool, okay. What needs to be changed? The sign needs to become a cos. The cos 2x now gets -3 as its coefficient. And the sine 2x now gets -2 as its coefficient. One more triple check. -2e minus 3x for sine, yep. -3e minus, yeah, cool. Okay, those are our equations that we're working with there. Let me section that off from this. What we'll notice is there are some similarities, which is that if we look at the integrals in part B, we'll notice e to the -3x sine, e to the -3x cos. The coefficients have been taken out of the integrals, the -3 and the positives 2 and the positive 2's. So there's a fair bit of similarities. Does anyone remember or have any recognition of what we kind of do in these scenarios where both diff and integral are in the same sort of question?
We make the diff thing look like the integral.
And make the diff thing look like the integral. Yeah. Will it be that? Yeah, the diff thing itself, like the left-hand side, I don't think will end up looking like the integral. But the right-hand side of these diff equations, they will have the integrals in them. And the reason why is the first step that we're doing here is integrating both sides. Right, if we integrate both sides of this equation, which we can do, what you'll find is integral of derivative just cancelled out. Right, so if you diff and integrate, you get right back to where you started. So these bits cancel and you're just left with these on the left-hand side. Everything else has an integral now. So all we do from there is continue to expand what that would look like. Now they do have those plus c's in there, which is technically correct, right? If you diff and then integrate, you do actually still have a plus c. That's why there's the c1 and the c2. So when we go ahead and rewrite this, which I'm hesitating to do at all, you want to put plus c's on those because you've now integrated. Specifically, you'll put the C1 and the C2 like they've written. So is that the ones I had it in? They had the C1 with the sine, they had the C2 with the cos. Yeah. Now, on this side of the equations, you'll notice very similar terms. So 2e to the -3x cos 2x, that's going to be, if we look back at the screen share, that last integral there. They've taken the coefficient of 2 out the front, and they've just left the function inside the integral. If you then look at my second part, which is -3e to the so on and so forth, that would be the first part that I have in the part B screen share. I'm hoping me just drawing that comparison is enough. Do you need me to rewrite all of that again so we can be super clear on how we transform what we have on the page into what's on the textbook? Or are we clear enough on the relationship between those? Because you do the exact same thing for the bottom one as well. Cool, okay. Hence show, and we've done exactly that. Part C, use the equations to determine the integral of e to the -3x sine 2x. Now, this is going to have mostly quite repeatable steps like we've done in similar questions to this. The fact that there's two functions in this case is a bit more worrying, because I believe we might be having to do a bit more than just work with one of them. So we want to determine what the integral of e to the minus 3x sine 2x is based off of these equations. Yes, we have a cas, and we could cas it, but it's telling us to specifically basically show that. What might we start doing to figure out what that integral is? And we can't just anti-diff it ourselves because we don't have a product rule equivalent for integration. There's no like lookup table that we can just use for this, at least not for methods. How might we start figuring out that integral?
Can we do something with the integration by recognition?
That's exactly what we're going to do. Yeah, this entire, like, part B was essentially the first step of integration by recognition, which is integrate your diff. The second part is rearrange at least one of these equations to start with until we get this integral on its own. We have a couple of ways of doing that. If you notice the integral, you got a copy of it here, and we got a copy of it here. Oh geez, I can't highlight that. There we go. On the screen share we have two separate spots where that integral exists. So just start with any of them. It's not going to really matter for now. And then we will take it from there. So, rearranging. Should I? Yeah, okay, let's just do it. So, rearranging the first equation, we're going to have e minus 3x sine 2x. Let's see, we wanted to have the sine one on its own, so we'll take this cos one over. So because it was plus, we're now minusing that integral, minus 3x cos 2x. And on the other side of that is the integral of minus 3 e to all that. What we're going to do is remove that coefficient, so dividing both sides by minus 3. So negative 1 over 3, all of that, oh there's a plus c in here too, my bad. Minus 1 on 3, all of that, and that's going to get us, yeah, integral e to the minus 3x sine 2x, which is what we want to have. Problem is this left hand side isn't fully simplified, especially given that we have a C1 in there. I wonder, do they actually need us to determine what C1 and C2 are? Because two equations, two unknowns, presumably you could if you simultaneously solve them. I wonder to what extent you need to do this, because it says use the two equations. Do we need to just do the exact same thing in equation 2 and then equate them? Because if you do, what we did was we rearranged equation 1 to get this bit on its own. We could also rearrange equation 2 to also get its equivalent on its own. And because you now have two things that say that integral is equal to something, it now means that those two things become equal to two rearranged expressions. Challenge is, you've now got C1 and C2 in the same equation. So...
I don't get what the question is asking.
Yeah, I mean, that's what I'm trying to sort of go through as well. Like, to what extent do we have to determine this integral? Because in the broader sense, determine the integral just means I want to have integral on one side and then equals something. You know, if I said determine the diff of sine x, you would give cos. Determine this just means get that integral on one side and everything else on the other. Ideally, that other side should be fully simplified down as far as it can be. Which
So we're supposed to get two different equations, answers that have one on one side have the same thing. integral e minus 3x sine 2x.
I think that's going to be...
Everything has to be on the left side or whatever.
Yeah, I think that's going to be part of it, because ultimately we want to have just one final expression, which is integral of e to the minus 3x sine 2x is equal to this.
Mm-hmm.
Now, the challenge that bars us so far is that we've got a C1 and a C2 in there, which we're going to need to solve. As soon as we know what C1 and C2 are, we now have constants, and we should be able to take it from there. Now, how we're actually going to do that is a mystery to me right now. Because we can do that in two separate equations and then equate the results together, but that's just going to get C1 and C2 together. We need one that has C1 and C1, just C1 in there, or just C2 in there, that we can now solve. I am just going to cheat a little bit and have a look at the answers, just so we can move things along for that. Do we need to solve C1, C2? Oh, they did actually want us to do that, holy shit. Okay. That's going to be a lot of writing. Let me have a look. Where are we at specifically? Part C. Okay. I think for this one, I'm just going to pull up the answers and then explore what they've done. So they did, in fact, care for us to solve for the C values. So what they've done to make life easier is they've started by replacing these big integrals with just a quick substitution, A and B. Then from there, the rearranging of this becomes less painful. Now, what exactly are they doing from here? They're doing... Okay, multiply equations here, and elimination method. Okay, what exactly are we eliminating here? If we multiply this one by 5 and... Oh, hang on, where's 5 and 2? 5 and 6 I'm assuming are these, because these were labelled 3 and 4. So 5 and 6, multiply that one by 3, that one by 2. What's that going to do?
To cancel out the B.
Oh, yeah, okay. Right, because I was looking at these and forgetting they were different letters. Yeah, okay, cool. We're cancelling out the B. Nice. Good pickup. By cancelling out the B, you now have an equation with A's, X's, C1, C2. This is further simplification, but then plugging in what A actually is. That's where this integrals come back. Same. Okay. Hence, integral of that is equal to that. Oh, so they didn't want us to find C1, C2. They just... Yeah, okay, never mind. So all of that... I wasn't entirely sure why they want us to stop. Apparently they just figured, hey, let's make it look complicated and then stop there. When in reality, if you're just going to put C1 and C2 in there anyway, you might as well just stop where I stopped, which was just rearrange one of the equations. I'm not fully convinced why this is more simplified than the other one. I guess you somehow combine the two equations together, but, you know, we could have done that by our substitution method we were going to talk about. So I guess this is just an elimination approach rather than a substitution approach. Cool. Yeah, that's definitely a tougher one for sure. I wasn't super clear as to how far they wanted us to go, whether it was even possible to cancel out the C1, C2. But they just said, nah, stuff it. Just call it capital C and then hide it. Jeez. Yeah, not a likely thing to happen in the exam or SAC at all, but I guess it's worth exploring a little bit about how substitution and elimination can be used even in complex equations like this, and also how you can use the like replacing those big terms with just simplified letters. Like a is that whole integral. It makes your math a lot easier. Cool. Okay. Next up. Actually, how are we going for time? Yeah, okay. We'll be right. Two curves intersect at a point. If x equals a at the point of intersection, okay, so this has an x-coordinate of little a, find the tan of a, and hence find sine and cos of a. Yeah, alright. Why not? Well, we can find little a pretty quickly. We have the two functions, and little a is just the x-intersect of the two functions. How would we find little a to start with? Because part of solving for tan a requires us to know what a actually is. And if a is the intersection between two known functions, the question then becomes, how do I find the intersection of two known functions?
We equate them together.
Equate them together, that's it. Function 1 equals function 2. H equals I. That's going to get us a general solution. So what are we going to do to convert this general solution into a specific one that we find useful?
Restrict domain.
Restrict domain. Yeah, what's a good domain for this one?
0 to pi.
0 to pi should be enough.
Pi over 2.
Yeah.
Yeah, it's just pi. Yeah.
Pi over 2. So 0 to pi probably still will be fine, because the period of these is 2 pi, so you'll still be relatively okay. But yeah, using the exact domain in the question gives the best results. Now, still not an exact, well, that is an exact, but still not a nice number necessarily, but we don't need it to be nice. We just need to find tan of it. So if we know that's a, then tan a is going to be as simple as just grabbing a copy of that and removing the x. Whatever comes out, hey, that is actually kind of nice. 4/3. And you might want to do a quick, well actually maybe not. I was going to say a quick sanity check by looking at the graph itself to say whether or not that makes sense, but it's kind of hard to say whether it's going to make sense. I was initially thinking tan is gradient, so just look at the gradient of the line, but the reality is one of them's going down, the other's going up, so you're not actually finding gradient of any of these lines necessarily. Because the angle, the A, is your x-axis. It's not actually the angle of any of these curves. So 4/3, you just kind of got to have to take it. One point of failure here would be whether you've got your calculator in degrees or radians. Because your domain is in terms of radians, make sure your calculator is in terms of radians. Anyway, cool. Next up, hence find sine A and cos A. I mean, you should just be able to plug that into the CAS and be fine, and be fine, but maybe they didn't want us to do it by tech active. If they didn't want us to do it tech actively, yeah, I suppose all of this could have been done, well, maybe not, because unit circle. Let's try and think of a tech-free way, potentially, to do this. We know what tan is, and we could, yes, just shove those into sine and cos, shove the same A angle in there. There's another way of going about it if I suddenly rip the CAS out of your hands, or let's say the CAS died. Think about the relationship between tan, sine, and cos.
Well, tan of tan of x is the same as sine of x over cos of x.
Perfect.
So
Yeah. So what's that gonna do?
So A is just going. You can just shove the whatever's inside the tan.
Yeah, so that was like the immediate easy way. If you have a cas, you just shove in the same A into sine and cos, yeah?
Sine of A is going to be 4 and cos of A is 3, right?
Yes, there you go. Because we had tan is 4 on 3. So tan is 4 on 3, but so is sine over cos. And just by looking left to right, you can say that sine is 4, cos is 3. Obviously that's going to break. But yeah, if I then go ahead and, just for a quick sanity check, see if that works out. We hope it does. Wait, what? Fourth this. Oh, right, because... Yeah. Because it can't be, because unit circle only goes from 0 to 1. Yeah, okay, let's, Okay, why has that happened then? Why divide by 5? Why divide by 5? Okay, so we have tan being...
We found the sine divided by cos, so like the denominators like cancel.
Yeah, the denominators do cancel, exactly, but like why divide... Because like if I, for instance, had like 4 over 20 and 3 over 20, presumably that's also valid, but it's not, because we've got to fit it in the unit circle as well. This is... What's this similar to? This is similar to those questions where as soon as you find... You have like sine equals something, cos equals something. It's the trig identity, actually. It's cos squared plus sine squared equals 1. And you rearrange from there and fit your values between 0 and 2 and pi over 2. How are we going to do that here? So we have tan is 4/3. That means sine over cos is 4/3. Is there a tech-free way of doing this? Damn, that's going to be a bit disappointing that we finish off with the...
From what I don't know if it will apply here, but like there were like identities to like map sine to cos or cos to sine.
Yeah.
Like, plus or minus pi over 2. Something like that.
Yeah, I've pulled up the screen share for the answers. They've done considering the triangle. Now what do they mean by considering the triangle? They've done a triangle with 3, 5, 4. Oh right, because okay, now that's kind of cool. So if cos is your horizontal, then cos being 3, sine being 4, because sine is your vertical. If you think about the hypotenuse of that, you therefore complete the triangle and therefore can get your ratios off of that. That's kind of nice. Yeah. So knowing the absolute lengths of them for the triangle would be 3 and 4 respectively, and then completing that from there, you get your hypotenuse as your denominator. That's kind of a cool way of doing it, I think. The way that I was sort of thinking it comes closer to would be, if I pull back the screen share, where is it? Circular functions, it's I think in the symmetries. I was thinking sort of like this stuff here, where you're told cos or sine is equal to a particular thing and you're given the domain, you can therefore find the other 2 remaining ones. The reason this doesn't work is because you need the sine or the cos, not the tan. Because for these, once you have the cos, you put into cos squared plus sine squared equals 1 to figure out the other one that you didn't have, and then you divide the 2 to get your tan. So this is similar, but different. This is where you have sine or cos. The one we just looked at was where you had tan, so you got to complete that triangle. Okay, I think I'm going to put that in the notes. I'm going to go to the trig stuff, the circular function stuff, and put that in our symmetries thing as a solution, a viable way of going about it. Cool. That's actually the first time I come across a question like that. So it's nice to have that every now and then. Cool. Alright, we ran over, so apologies for anyone who had to be anywhere after this. I can stick around for a tad bit longer. I do have a call after this though, so if there are any things I should clarify further, let me know. I'll be sure to do it in the time that I have. Otherwise, thanks for coming.
Okay, thanks. Have a
Thank
good
you.
day.
You too.
Thank you.
Thanks.